Let's look at an application of Fourier transforms used in nuclear magnetic resonance spectroscopy, or NMR, which is a powerful tool that helps determine the structure of whatever analyte or chemical that is being observed. Essentially, what happens is that a molecule is put into some magnetic field, and an impulse of electromagnetic radiation, radio waves, is sent into the molecule or the analyte, and a pulse signal or a signal is made that degrades with time. And through the power of a Fourier transform, we can convert this signal from the time domain into the frequency domain. Essentially, that signal that gets released as and decays with time is represented by this formula, where one term represents the position that our signal occurs along the frequency domain once we take a Fourier transform, and one term that tells us the shape of the line, whether we're going to have singlets, couplets, triplets, or however the multiplicity ends up being. Taking the actual Fourier transform of that signal function ends up giving us a nice combination of an imaginary part and a real part. Therefore, the raw spectra that we actually originally see is going to be that linear combination. And after breaking it into its real and imaginary components, we get the meaningful real component, or the real component that can be plotted on a spectra. And why this is actually very powerful is because performing a Fourier transform on an NMR signal, converting it from the time domain to the frequency domain, actually allows us to determine if it's proton NMR, all the unique proton environments, the amount of protons in each environment if we take the area under each peak, and by the multiplicity, the actual number of hydrogens near or adjacent to each proton environment.